Nicolas Pitre. I've been working on trying to shrink the Linux kernel for IoT purposes. And it turns out that I found a couple of ways. So I'll discuss why we should do this, how it can be done, some of the problems I've encountered, and the solution that I found so far. So slide number 3, please. The reason we should do this, it's because if we want to help the traditional embedded distributions like Octo or OpenOCD, it's very useful to be able to shrink the kernel, because then you could extend the life of existing products by making space for new protocols or new functions while using the same hardware. So that's one reason to shrink the kernel. Slide number 4, please. For IoT purposes, IoT is going to be very pervasive, where we will see many things connected to the network at some point. We can think about all our phones, our routers, or even cars, washing machines. I've seen one. And of course, if we see all those things everywhere, they're going to be very cheap. Slide number 5, please. The problem with that is security. If we have cheap gadgets over there, they need to have very little RAM. And the problem with that is if people start to implementing their own kernel and their own software stack, it is going to be insecure. We know because there are many examples of high-profile operating systems right now which have security issues these days. So imagine if you try to roll your own. So be able to upgrade gadgets in the field with new updates to fix security issues. It's something which we really need to care about. We cannot avoid upgrading IoT in the field, right? Slide number 6. The other problem with that is legacy software maintenance is hard. It is expensive and especially uninteresting. People tend to focus on the latest product and they don't maintain the existing products very well. So we really need to have a solution that revolves around custom software. No, that's the opposite. Avoid custom software. So if we can leverage existing operating systems such as Linux with a lot of people around it, it usually helps bringing the cost down. Okay. So as I said, slide number 7, please. As I said, Linux is a good solution because it has probably the best looked after IP stack in the world. It has a lot of storage options. There's a large community around it, and it's often found into embedded setups. The problem with that, number 8, Linux is big, right? It's being tuned for high-end applications, high-end servers, and it scales up more than it scales down. And often in embedded setups, the Linux kernel is usually the biggest component of the whole system. So shrinking the kernel is really part of the solution. Number 9, please. So there's a website called elinux.org. It lists a bunch of things that we can do to shrink the kernel. For example, we can have kernel XYP, but that reduces the amount of RAM it uses, but it's going to use flash memory. So it's not actually shrinking the kernel. Some people are also talking about user space IP stack. The thing is, if you require an IP stack, whether it's in user space or in kernel space, you still need an IP stack. So there's no much gain to move things around here. It's probably better to try to configure the existing IP stack and not create another custom solution. We can do specific kernel configuration, but this is quite hard because someone has to go through the code and see what can be configured out. Still, there are probably low-hanging fruits, like trying to string the kernel with automatic means, such as LTO. Is there someone who doesn't know what LTO is here? Yeah, okay. Oh, by the way, probably you noticed, but I'm blind, so I can't see you. If you want to participate or ask questions, please do interrupt me. Pardon me? I don't hear you.
Explain LTO.
Okay, I'm going to explain it. So, slide number 10. LTO is the recent feature in GCC. It means link time optimization. So the thing is, we usually have one C file, and if we use a static function in that single C file, whether they're brought into that file with include files or whatever, if static functions are not used, they're being compiled away, optimized away at compile time. The thing is, if we do have external functions, then GCC cannot know if those functions are going to be referenced afterwards. So they're not optimized away, even though they might not be used at all in the kernel. So what LTO does is to simply parse your C file, and it stores into the object file only the internal representation that GCC uses. At link time, it will bring all those internal representations together, and then, only then, it will go through all its optimization passes. And then it will do constant propagation, it will do dead code elimination, and so on. So if you have external functions that are never referenced, at that point, GCC will simply skip them as if they were all static functions that are never called. So this is really, really nice because it's very effective at removing code which is never referenced. Problem with that, slide number 11, please. LTO has many drawbacks. It's still a bleeding edge feature, so it means that it's not yet as stable as standard compilation. It is slow, very slow, because you cannot optimize your kernel in parallel like we do with standard compilation, because then we can do in parallel on multiple CPUs. If we parse and optimize a single file, it can be done in parallel. But if you need to wait until you concatenate everything together in a single representation to optimize things, then it's all serialized at link time. So that's probably the biggest drawback of LTO. For example, on slide 12, here I made some timing of kernel compilation with and without LTO. So for a standard build on my own machine, it would take about 5 minutes for a standard kernel build. With LTO, it's up to 10 minutes and a half. would say, okay, that's almost twice the time. But the thing is, if you do a single change in your kernel, and we do that often, right? You change something, compile, test, kernel crashes, do another change, compile, test, it crashes again. Well, you know the drill. With LTO, if you do a single change, it has to re-optimize the whole thing, because once again, it will only parse the C file and then concatenate all the internal representation before doing the optimization. So with a single change, I needed to wait for 6.5 minutes, even if I only moved a print key somewhere. Whereas with the standard compilation, it's 12 seconds. So for kernel developers, this is certainly a no-go. Okay, so slide 13, solution for that. This is what I call a poor man's LTO. The idea is to, okay, let's start with some simple code. Right now, if we look at the code that I presented here, I have two functions. They are being stored in .text section. So far, so good, right? Slide 14. There's a function in the linker, in the compiler, please, sorry, that tells GCC to assign a different section to each function. So if we remember the code that I had, the foo function would get stored into .text.foo, and the bar function would get set into .text.bar. Slide 15, please. We can do the same thing with data. There's a switch, the F data section, that will store global data into their own sections as well. Then, if we move to slide 16, we can make this into a simple test program. So if you look at this, the main function is not calling the bar function. So this is a function which is not referenced. If we compile this, the program runs, but even though the function bar is not used, it is part of the final binary. Slide 17, please. Now, if we go to the linker, it has a feature that discards any section which is not referenced. It garbage collects it. So if we use that switch on our program, we see that the bar.text.bar section is being discarded, and with nm we see that bar symbol is not there anymore, even though it wasn't a static function. So, slide 18, please. How does it do on the kernel? Okay, to start to test this on the kernel, I wanted to have the smallest kernel possible to start with. So I compiled myself an all-no kernel, all-no config kernel, and surprisingly, that kernel with everything that can be turned off is being turned off. The kernel binary is still 850 Ks in size, which is way too big for a kernel that apparently cannot do anything, almost. So what can we remove from the kernel, again? So slide 19, right? Okay, so let's try to remove all syscalls. So you see the patch that I applied to the syscall entry path, which actually make all the system calls return nothing. That means that the compiler should, in theory, optimize away everything which is not referenced afterwards. If we look at the kernel build again, slide number 20, unfortunately, by removing the system calls, I saved only 5% of the kernel binary. And we're talking about a kernel that does nothing, everything has been configured out, and it has no system calls either. So in theory, you should have only a scheduler and a memory management, and we still have a big kernel. So let's see how the technique of using a GC section is effective on the kernel. So slide 21. It's pretty easy. It's only a matter of modifying the makefile to add the appropriate flags. So slide 22. Does it build? No, it doesn't build. So some people might have seen this error. It certainly rang a bell in my case because I'm the one who introduced that error maybe 10 years ago. So slide 33. There's an assert in the linker script that complains if some tables are empty. In the ARM kernel, we do gather tables for CPU support and for the machine architecture as well. So if those tables are empty, we complain. Those tables come from slide 24. That's one structure that every machine has to fill up. Well, it used to be. These days, it's probably generic because we're using device tree, but it's the same principle for CPU support. Slide 25. We have an example usage of that. And this table is being pulled into the binary by the linker. But the thing is, if we're using GC section, that table itself, it has no symbol in it. And it has no reference to it from the rest of the kernel binary. So that's why it gets garbage collected. So I spent quite a lot of time trying to find a way. I even considered modifying the linker to add a feature to mark some section as no garbage collect. Fortunately, I found that this feature was already implemented. Where are we? 26. Yeah, okay, 26. There is a keep statement that we can apply to sections in the linker script that would prevent them from being garbage collected. So, obviously, we apply that to our sections. And then, 27, success. We can build a kernel. So let's see what we saved. 28. It turns out that now, with only system calls being removed, we're at 95% of the original kernel. With garbage collection applied, we're down to 65% of the original kernel size. So this is quite effective because if we remove system calls, for example, there are support functions for those system calls that are shared between different system calls, for example. So even though if we remove the system call function itself, there are still functions that are there, not referenced anymore, but The only way to remove them is to apply this garbage collection. And it would be senseless to try to apply kconfig symbols into this, because this is the case for drivers as well. For example, if you have two drivers using the same infrastructure, this infrastructure might still be there even though you're not configuring in both of the drivers using it. So this problem of finding out all the support functions, it's not scalable if we do it by hand. It's better to use the computer to find out all those sections which are not referenced anymore. Right? Questions so far? No? Okay, so let's see if LTO, the original LTO, can do better. So, slide 29. Turns out that, in fact, LTO does a little better than our simple garbage collection. The thing is, even though LTO is slightly smaller, it takes much longer to compile the kernel. So the idea is probably to have both. During development, we can use the quick way, and for the final build, we can use LTO. Or even then, if LTO is not stable, we have a fallback. Okay, so 30, is that it? Can it be that easy, right? Not really, because as we've seen, there are tables that the kernel built, have been built from the source, and many of them exist in the kernel. So, for example, on slide 31, here's a list of many such tables that we have. So, for example, the exception fix-up table. Every time we call a put user or a get user, there's a fix-up being generated on the side, out of line. All the init calls, the vector table, the pointers to the dynamic physical to virtual patching at boot time. So all those things are tables that have no reference to them. They do have reference, they contain reference to the code, but not the other way around. So they get garbage collected if we don't keep them with the keep statement. Okay, slide 32. Problem with that. We have a problem with backward statements. Like I said, let's take a simple example here. So if you look at the put user function, it creates, if you look at the assembly down there, the put user function itself, it's really just a store, right? But all the exception handling requires a table there. So if you look at the assembly code, from line 10, we have the code that is being executed when there's an exception, a trap. And there's another section with a table of pointers from line 14. So all those things, they have pointers, like the, if you look at the label there, it branches to label 2 backward, or label 1, label 3 backward. So those things are creating dependencies on the function above. So slide 33 If we get many of those functions, we cannot garbage collect them anymore if they're not used, because the exception table is gathering a reference to all those functions. So the linker sees that they're being referenced, so it won't garbage collect them anymore. So we're brought back to square one. If we look at okay, slide 34, with a closer look at the put-user function. It gets integrated because we follow the code, slide 35. We're not down there yet, slide 36. Now we're at the bottom of it. As you can see, there is a special assembly section being used there, and that's how we generate all the exception table. How can we split that table? Because at some point we would like to have a way for the linker to discard unused functions and discard the exception table entry that goes with it. So, slide 37, we could modify put-user and add a new argument. For example, I could pass the function name down to it and down to the assembler. So there is an underscore function, but that won't work because the compiler presents that as a string pointer. So it's not a literal string. It's being declared as a pointer. So we cannot use that with the assembler. There is the legacy function in all caps as well, but it's the same thing. It's also a pointer. We could use pretty function, that's the same thing. If we use the file and line preprocessor macros, those are literal strings. Problem is, if we have multiple functions in the same file, they're going to have the same file name. So once again, we're going to pack multiple function exception entries in the same in a section with the same name, so we cannot garbage collect them. There's another macro which is counter. So it actually increments a number. The problem with that is that, okay, we have a counter, it always changes, so we're fine, right? The problem with that is that if we have a function which is being inlined, for example, if put-user is being used within the function which is declared as an inline function, and that inline function is used multiple times, then it won't have its own function section. The thing is, at that point, counter will have one value which will be repeated many times with different functions because of the inline. So we're back to square one. So all those things, I really scratched my head trying to find a way to distinguish those sections from the C code, and I couldn't find any way. So the solution, slide 38, right? Okay. Solution was to modify the assembler. The assembler knows in which section we are. So the idea is to be able to create a new section name based on the current one. So if we have .text.foo, and we want to have an exception entry for that section, we can just substitute the name of the current function section into the new section, right? So that's a feature that I implemented into the assembler. Fortunately, it was accepted upstream. Okay, 39. Turns out that this feature could fix a long-standing issue with the kernel as well, because I don't know if you noticed, but even though you have drivers built into the kernel, all the exit code is still part of the binary, even though it's never used. So if we want to shrink the kernel, it would be a good idea to discard that code and not compile it into the binary at all. Right now, it's compiled into the binary and discarded at boot time. The reason for that is, once again, if we use put user in exit code, it generates an entry into the exception table that has a backward reference to that code, and if that code is omitted from the binary, then we get a link error, because that exception table has a reference to standard kernel code as well as this exit code, which is not there anymore if we don't build it into the kernel. So with this feature, we can fix both of those issues. Okay. Slide 40. Now that we have the ability to distinguish different exception entry into their own section, the linker is happily garbage collecting them all. So we're back to square one. We're not going to have a keep statement on every section because they are now part of every function in the kernel. We want the tool to be able to discard those functions that are not used and have the exception entry being discarded with it. Right now, we're missing a forward reference to this exception entry. So if you look at the code, we do have a reference from the various exception sections, but not from the main code that we want to discard. So slide 41. Another feature that I thought about was like a tag statement in the assembler that would just produce a dummy reference. So if you look at line 6, I think, is there. So we produce a forward reference to the entry in the exception table. So if this function is being referenced in the kernel, if it's being linked, it will bring with it the exception entry because it has a reference to it. And if the function is being garbage collected, then the exception entry section will be garbage collected with it as well. So I started digging into the assembler and into libbfd, and it's way different from kernel code, I can tell you. So it took me a while before I could discover that, slide 42, everything that I needed was already implemented. So it's in the form of a reloc statement. With that, we can insert a dummy reloc that has a reference to the section that we want. And if the reloc itself is being garbage collected, then it won't have any reference left to the exception entry. So, once all those things are in place, this is only enablement to get to the interesting part. So, slide 43. If we want to have LTO and just this GC section garbage collection effective, we need to sort out all those, what I call those peg point symbols in the kernel. So one thing to look for is, for example, export symbols for modules. Every time we have an export symbol, that's a peg point. That's a reference to some code that could be garbage collected if that symbol is never used by none of the modules that you have configured in your kernel. For embedded systems, probably we need to have configurable set of system calls, because most of the time, and within an embedded setup, especially for the small gadgets that IoT is looking for, your user space is static. You can scan your user space for all the system calls that you require and discard all the other ones that you don't need. And if we push this idea further, we can probably put system calls into modules of their own. So if for example, if on your OpenWRT system, you want to install a new package that requires a system call that you don't have, then you just install the module for that system call. So those are very low-hanging fruits that will allow to shrink the kernel even further at that point. So, okay, 44, questions? Okay.
Hello, I have a question about maybe not related to LTO, but related to the size reduction. So we know there's a project called Colonel Compilation. So from your point of view, do you see LTO is a competitor against Colonel Compilation, they can coexist? For example, if LTO can, if with LTO we can get a very small size kernel, the Colonel Compilation project may not make sense anymore.
Well, I think that LTO and any tinification effort are complementary. LTO is one of the tools that probably allows you to do things. For example, I think at some point we could have less configuration symbols and be able to discard features in the kernel much more easily with the help of LTO or GC section. They're not in competition. I think it's one way to achieve tinification. Because then if you want to tinify your kernel, you need at some point, even though you're using LTO, you have to go through the source code, make sure that all the functions that you don't need are not being referenced anymore, are not compiled into your kernel configuration. So using LTO, it's a nice way to be able to, okay, I removed function A, I removed function B, and all of a sudden function C, D, E, F are being garbage collected away because they were only referenced by A and B initially. So it makes things easier afterwards.
Thank you.
Do you think using LTO even could have good benefits on performance?
It does improve performance somehow, because it doesn't only remove unreferenced code, it does constant propagation. So if one function is being called with a constant value all the time, then GCC will propagate that constant down into the called function and optimize things appropriately. So, for example, if you have a switch statement and that constant is being passed to the switch statement, then all the unused switch clauses will be optimized away. So it helps for removing some of the conditionals in the code.
Okay. And I was thinking about the cache hit rate that could be improved, for example.
The cache?
The cache.
Cache, well,
since it would be smaller, you would
obviously, if your kernel is smaller, the
yeah.
cache footprint will be smaller as well, so you have a greater chance to fit into the cache. But I think that the best performance gain that we'll get is through the fact that you can optimize the kernel as a whole instead of optimizing every C file individually.
Okay. Thank you.
But I think that some people did some benchmark on standard configuration kernels on x86. And one reason why LTO is still not merged upstream, it's because the performance argument wasn't that compelling. It's not much of a gain for a server or a big machine configuration. Whereas it could have lots of benefits if our goal is to shrink the kernel size. There is very effective. Any other questions? No questions? Thank you very much.